data somehow into two clusters and then just take the sample.
Exactly. So Dasgupta's strategy that we talked about last time was, given a large enough set of samples from a mixture of two Gaussians or a mixture of many Gaussians, cluster that set of samples exactly into which set of samples was generated by which components. And then all you have to do is you can output the empirical mean and empirical variance and empirical mixing weights, and those will, with high probability, be good estimates to your true parameters. But we also saw a limitation last time that, what are we really requiring in order to even realize that plan? We need that for a mixture of two Gaussians that the two components have very little overlap, that they have vanishing overlap, because as soon as they have some non-negligible overlap, we very quickly get samples in the overlap region, which even information theoretically, we can't figure out which one actually generated. So that was last time. At the very end, we talked about a different way to sample from a mixture of two Gaussians that explicitly samples from the overlap region without deciding which component they came from, and otherwise samples in the right way from the non-overlap region in such a way that the overall procedure really is a faithful sample. So, the lead up is that we're really thinking about, for the strategy of clustering samples, we can only do it in settings where the components have negligible overlap. But what we're going to see today when we look at high-dimensional mixtures of Gaussians is that there's some really surprising settings. This is sort of a pathology or counterintuitiveness of high-dimensional geometry, that they're actually very interesting settings of mixtures of Gaussians that have very little statistical overlap, so that you really can realize Dasgupta's plan. So this will be the clustering-based approach for mixtures of Gaussians. So the quick reminder, to cluster all samples, let's say all M samples, with high probability, we need that the total variation distance between the two Gaussians, the PDFs rather, is much smaller than 1 over m to have any hope of doing that, if we're doing it for m samples. So we need, inverse poly size total variation, is at least 1 minus 1 over m. So we need the total variation distance to be close to 1, that they're almost entirely disjoint in the relatively high probability points. Okay? Or rather, you need 1 minus the total variation distance to be much smaller than 1 over m, to have any hope of realizing Dasgupta's plan. So today we're actually going to realize Dasgupta's plan in high dimensions. So let me quickly remind you what a high-dimensional Gaussian is, but really today is about trying to understand the counterintuitive properties of high-dimensional Gaussians. So an n-dimensional Gaussian is parameterized by its mean, mu, which is just a vector in Rn, its covariance matrix, which is an n by n matrix, where sigma is PSD, in order for this to make sense, and its overall PDF is just the following simple formula, which I think we've already covered, but let me just state it again for completeness. So its PDF is some normalization where you have this exponential decay. You're really taking the quadratic form, of x minus mu on sigma inverse. So remember that when we were in the one-dimensional case, we're dividing by little sigma. But in this case, now we're actually just taking the quadratic form on the inverse of the covariance matrix. So that's important. And then you have these extra normalization factors in here. So this is the formula for the PDF of a Gaussian. But just to remind you, so we'll call, so if sigma equals sigma squared times I, then we'll call this a spherical Gaussian. And in fact, it's easy to check. That in that case, in the case of a spherical Gaussian, its PDF actually factorizes. So when we plug in little sigma squared times the identity for the covariance matrix, then what we're going to get is we're going to get independent marginals for each of these random variables, where each one, the ith dimension is going to have mean mu I, sigma squared variance. And in this way, it really is, so what this means, by virtue of the PDF factorizing this way, it means that it's independent coordinates, right? So you generate a sample from a high-dimensional spherical Gaussian just by sampling its coordinates independently, according to the Gaussian with the right mean. But one of the other things to sort of connect this to other things we've talked about is that you remember when we talked about independent component analysis, well, we need this notion of things being non-Gaussian. So in this case, for the spherical Gaussian, the fact that it factorizes this way means its coordinates are independent. And it's also easy to check just from this definition that it's invariant under rotations in the case where it's spherical. And remember, one of the crucial things we were using when we talked about ICA, just to connect the two pieces together, was that we were relying on any distribution which has independent components and is invariant under rotations must itself be a spherical Gaussian. So that was one of the key properties we used. So we won't need that right now, but that's just to connect the different things we talked about. All right, so what we're going to do now is we're going to develop some of the basic facts, because some of these things are, some of the facts about high-dimensional Gaussians are immediate from your intuition from the one-dimensional case and really do carry over. Some of them don't. That's what makes clustering in high dimensions interesting. So let me describe some of the basic facts about Gaussians, and then we're going to use them and actually follow Dasgupta's plan and get an algorithm for clustering high-dimensional mixtures. So let's start with basic facts about Gaussians. So let me even start with low-dimensional Gaussian before we work up the interesting properties in high dimensions. So let's say X is distributed according to n mu sigma squared. So it's in one dimension. Then, if we take X minus mu over sigma, this itself is a random variable which is distributed according to a Gaussian. And can anyone tell me what its parameters would be?
0, 1.
0, 1. Right? So it's obvious that when you subtract off mu from this, you're really just affecting the mean. The other thing I want to emphasize that when you want to correct the variance, right? The variance is a measure of x squared. So to correct for the sigma squared variance, you divide by sigma, not sigma squared. So that's the important thing to emphasize, is that this is the transformation which allows us to put a Gaussian into standard form. But we're going to use this transformation in different ways. So let me call it, fact 1 prime, I guess. That just applying this more generally. So if instead we have X is again distributed as mu sigma squared, then Bx plus A. Can anyone tell me what this should be distributed as?
mu b plus a b
Yeah.
squared.
So b mu plus a is definitely the mean. One way of thinking about this, let me just sketch why you should see this, is this is going to be a Gaussian variable. That's not so hard, and it's just the basic fact that affine change of variables are going to preserve your Gaussianness. But then, if I already tell you this is a Gaussian, all you should need to do to figure out what its parameters are is to calculate what its mean and variance are. So it's obvious that when you calculate the mean of this, that's exactly what the mean is, because the mean of x is mu. Now, the same way you can calculate the variance so the point is that a here is not going to affect at all what happens to the variance. And so what happens to the variance here?
B squared.
Yeah, exactly. B squared sigma squared, right? Good? All right. So this is just fact 1 prime. So these are just the change of variables that we're going to use and sometimes. Not too bad. Fact 2 is also easy. These are all just the intuitive facts. Before we get to the third fact, which is the more interesting one. So this also, your intuition will be spot on from low-dimensional Gaussians, that n of mu sigma x, a PDF is itself maximized at x equals mu. This is also very easy to check. All you would do is you would differentiate the PDF and set it equal to 0, and lo and behold, you would get that it really is, the mean is itself the single most likely point. So that's not so bad. Now let's get to more interesting things, because clustering in high dimensions is all about concentration of measure and some of the somewhat surprising facts there. So the fact which we're going to, well, sort of prove, I'll tell you why it is true by connecting it to something else. Well, if you take x minus mu squared, then what do you expect this quantity to behave like? Let's say, sorry, if x is sampled from n mu sigma squared I. So what do you expect this quantity to behave like? In this case?
A Gaussian centered at 0? Something like that?
This magnitude. So this is just a, what do you roughly expect this value to be? So I'm saying typically. What's its expectation? What was that? Sigma squared f. But the important thing is that it actually doesn't deviate too much. That it roughly behaves like
I see.
this quantity. So it'll have this type of standard deviation. So and then the probability that it is any larger than that is going to be, have this sort of exponential tail bound. Okay? So, the way to think about this fact that's sort of immediate from a probabilistic standpoint, we're going to, show it why it is true. It's a good reason to talk about what's called the chi-squared distribution, which is exactly why this is true. But, the way to think about it is that when you sample from the spherical Gaussian, all of your mass is concentrated in a sphere of radius sigma root n. And in fact, it's a very thin shell of that sphere. So a Gaussian is, even though its maximum value is at mu, it itself, you can think about it as like a random point from some very thin spherical shell of this radius sigma root n. So at first blush, fact 2 and fact 3 seem to be a bit contradictory, but why can they both be true? Why is it true that the maximum, probability point is at the mean mu, even though you should really think about a sample as behaving like a random sample on a sphere around that point?
Almost all the volume of a sphere is near its boundary.
Exactly, right? So that's the sort of pathology of some of these high-dimensional things, is that, you know, in one dimension, you really do expect a decent number of samples to be pretty close to what the mean is. But now in high dimensions, what's going on is even though the maximum, you know, value point for the PDF is still at mu, there's so little volume around there that you should, you know, at some point you're growing the volume so much that you're washing out the fact that you're decreasing the PDF. And the result is that a sample from a high-dimensional Gaussian is a sample from a very thin shell sphere. So that's what this probabilistic statement means. That's something that we're going to exploit. Let me sketch, you know, the proof. You can prove this, you know, any way you want. But you know, maybe one of the nicest ways to prove this is to introduce what's called the, you know, chi-squared distribution. So the idea, and this is really just a proof sketch.
Anchor?
Yep.
Quick question. Sorry. Maybe it's because it's really counterintuitive, but so in the sphere, there's not a lot of density in a high dimension? Or
what do you mean?
Maybe I didn't understand what fact 3 means. Can you
Okay.
explain it again?
Yeah. So if you think about X as being sampled from this spherical Gaussian, what this fact really means is that you take a polynomial number of sample of your points, and in fact, all of them will be in a sphere centered at mu, whose radius is sigma root n. But in fact, not only will they be in that sphere because this value cannot be too large, it also can't be too small. It really will be around sigma root n. So it's kind of like you're taking the sphere and you're taking a thin shell of it, you know, which corresponds to what this quantity is, rather the square root of it. And what's going on is that you're entirely in this thin spherical shell around this Gaussian. So you get almost no points, you know, from half the radius, for example. It is. Oh, it is. It is. But I think, so this in fact is a nice enough random variable that it actually has an analytic closed form. So, you know, you could prove this via Chernoff bound, and that's fine, right? But you could also prove this just by knowing that the, you know, if you have a sum of Gaussian random variables, the squares of Gaussian random variables, it's called a chi-square distribution. So that's important enough that I at least want to state that, you know, what a chi-square distribution is, what its limiting properties are, and you can think about fact 3 as a corollary of that instead of as a Chernoff bound. So it's just another way to think about the same thing. So, you know, what I'll be using is, so we'll consider the following sum of, you know, xi minus mu I squared over sigma squared. Now this quantity is equal to 1 over sigma squared times x minus mu squared, just the way that I've defined it. But the important point is that now we can define zi to itself be xi minus mu I over sigma. And what's the distribution of zi? Standard normal. Exactly. So that's fact 1. So it's a standard normal. So in fact, so we have here in understanding this as a then proxy for understanding what this term behaves like, this is actually the sum of the squares of standard normal Gaussians. That's called a chi-square distribution. So let me define that, but I won't go into too much detail on it. So summation zi squared I equals 1 to n. Where each zi is a standard normal, is called a chi-squared distribution. With n degrees of freedom. That's just what it's called. This is a chi-square distribution, and the way that you describe its parameter is whatever that parameter is, how many of these standard Gaussians you're taking the squares of and adding up, is the number of degrees of freedom of the corresponding chi-square distribution. So the same way that you could just analyze these things through Chernoff bounds, it's good to know that actually when you encounter sum of squares of Gaussians, it itself is a very well understood distribution. You can write down analytically what its PDF is. It's some expression that's not too much more complicated than what a Gaussian looks like, but looks a bit different in some regards. But there's some important facts about about chi-squared distributions. Let me keep this up, I guess. And do the following. So the key fact about chi-squared distributions is summation zi squared I from 1 to n minus n. So remember that the expectation of this is n, because each of these zi squareds, its expectation is 1 by virtue of it being a standard Gaussian. So you subtract off its mean, and then the key point is you normalize by 2 root n, and that converges as n goes to infinity to itself standard Gaussian. So this is just the basic fact of central limit theorem on these chi-square distributions that you can check this. Yep.
Is that in the sum or sum minus n?
It's oh, sorry. You meant, yeah, it's like this. So you need to correct for the mean. So the reason it has to be outside the sum is otherwise the mean would be non-zero, and you'd never be able to converge to that Gaussian on the right. So, but you can check that it really does have the right mean and variance, and it's the sum of independent things, and it converges by central limit theorem to this. But this is immediately going to imply fact 3, because what we end up getting now is then the summation zi squared, well, it behaves approximately like a normal, which we can move the mean over now just using, for example, fact 1 prime. And what's going to happen to the variance when we multiply it out is we're going to take the sigma squared here, so we'll get 4 times n. 4. And so what all of this then implies is if we go back to x minus mu I, x mu I squared, then this quantity itself is going to be also approximately normal. But now where we multiply by sigma squared n, because we're removing the sigma squared down here, and we're going to get a 4 sigma to the 4th n, because these two quantities differ by this sigma squared in the denominator. So we're going to pull that out, and it's going to affect the mean just by multiplication, and we're going to have to square whatever our normalizing factor is in order to affect the variance. So all of this now is going to directly imply it, because the way to think about this is that this quantity behaves like it's centered at its true mean. So when we're subtracting this thing off, the rest of it is just a tail bound, because this is our variance. So we should really look at square root of this, maybe times an extra root log n, to make sure that we have inverse Pauli tail bounds. But that's exactly how you get fact 3, is just from these properties of chi-squared distributions. So then, standard tail bounds then imply that the probability of x minus mu squared minus sigma squared n being larger than some c sigma squared root n log n is itself roughly upper bounded by e to the minus c squared sigma to the 4th n log n. That comes just from how much you're deviating here. and then divided by the overall variance, so we end up getting this 4 sigma to the 4th n. And that's exactly what we were looking for. We get a n to the minus c squared over 4.
That's true the limit.
Yeah. So all of these things, that's why I had to use approximation here, is that this limit is true as you take n going to infinity. You have to be a bit more careful about what these are, but I don't want to go through the full proof of just the tail bound, but this is the sketch for why you should think it's true, is anytime you see the sum of Gaussian, squares of Gaussians, first thing you should think is chi-squared bound. That'll tell you what sort of normal you expect it to behave like, and that's really all we're using for this property. So I could do that via Chernoff bound, but I can also do it through chi-squared. But this was really just meant as a sketch in any case. So does this make sense then? These are the basic facts that we're going to be using now. So let's see, what should we do? Let's do a vote. So let's say we have some mixture of Gaussians in high dimensions whose PDF So we want to know when, actually let me even say it's inverse poly. Pop quiz. So, really all of this is relying on the idea that we have, let's say, a mixture of two Gaussians. A lot of these things will work for mixtures of many Gaussians. That's not really a big deal. Let me keep it as two Gaussians for simplicity, though. So we have these spherical Gaussians. And you remember your one-dimensional intuition that if you have these two Gaussians with the same variance, you roughly have an idea of what it takes for them to have virtually no overlap, right? We know that we need one all the way over here and one all the way out there, and we really have to be able to see two distinct humps in the PDF in order for that to be the case, right? So we know what sorts of separation we need in order to hope to do clustering in low dimensions. What about in high dimensions? So we have mean mu1 and mu2. Doesn't matter what the mixing weights are. That's just to set up what the mixture is. And we care about is these two components which both have the same variance, sigma squared I. And now we just proved some properties about what these Gaussians behave like spherical balls with, whose mass is distributed on some tiny thin shell. So the question is, when can we expect that their total variation distance is tiny? Tiny enough that we can cluster. So A, what this means is that the two balls are just disjoint, right? Because the balls are radius sigma root n, because we would take the square root of that sigma squared n. Or, it could be much closer, sigma n to the 1/4, or it could be sigma log n. So who votes A? No one votes A.
So the question is when we can learn them, distinguish them, right?
No, this is just a theory. This is just a information theoretic question. So in order to hope to cluster these things, we need the total variation distance to be tiny. Sorry, did I misphrase this? My mistake. What I want is I want their total variation distance to be 1 minus 1 over poly. I want them to be almost entirely disjoint. So I want 1 over poly n overlap between them, so I have a hope of clustering. You all know what these pictures should look like for this to be true in 1 dimension. Now, so Brenda, what was your question?
I don't remember.
Okay. So this is purely an information theoretic question. I'm not saying I necessarily have an algorithm for doing each one of these things. Yeah?
It's the square root n.
That's what you think? Seems pretty reasonable, right? Especially since the balls, I'm ignoring polylog factors here. So especially at that point, the balls really are not touching, right? So these spherical balls. So it seems like A, right?
I vote B.
You vote B. Why do you vote B? You can't just say because it's different.
No, because A, you're
You
saying A is separated, right? But the small shell only is a very small intersection. So you're not, it's still kind of okay to
that sounds
have them
interesting.
close.
So
but that's too
whose
close.
mind was changed by Brando? Who votes B?
B.
B?
B is true and A is true as well.
Oh, yeah, that's fine. I mean, what's the small? Fine. It's a multiple choice thing.
A is the safest answer.
You're in the wrong school. It sounds like a slum answer. What about C, though?
Too close.
You vote C?
Yeah.
C? C? Why? Just because you're optimistic? C? Why?
Well, it should be like roughly the width of this spherical thing, and that looks like it's got a limit.
Yeah, so actually, it turns out the answer is C. But what's funny about this is that these were all different limits in algorithm design for where people worked up until. Now, everyone knew what the information theoretic answers were, but each of these are themselves not the limit of this question, but the limit of some other approach. So this approach right here, we all know what this approach is. That's the limit of when the spheres are actually disjoint. We're treating each Gaussian as some sort of distribution over a thin spherical shell. And at this point, the spheres are just disjoint. At this threshold, as Brando described, actually, they're not disjoint anymore, but the actual volume of their intersection is small enough that it's inverse poly. So this is actually the threshold at which when you take a bunch of samples, every pair of points that comes from the same component will be closer than every pair that comes from different components. So you can just do simple distance-based clustering. Actually, that fails beneath this threshold. It's just flat out not true. But it's because you haven't identified what are the directions which you should use to actually separate the mixture. If you actually use the line connecting the two means, then you can actually get much better separation. So there are algorithms that go all the way up into this point, and that's what we're going to cover. It's actually pretty simple. Just going to use these basic things. So I mentioned I have a plane to catch, so I have an incentive to do this quickly. So, this result is the result of Aurora and Canaan. It's a simplified exposition of their proof, a simplified setting. But what we're going to show is that if mu1 minus mu2 is at least n to the 1/4 sigma root log n, then there is a polytime algorithm to cluster the samples. And we're just going to use FAT3. That's it. So the proof of this is actually surprisingly straightforward. It's a very simple proof. So what we're going to do is we're going to consider the following thought experiment. Our strategy is to hope that every pair of samples that comes from the same component is closer than every pair of samples that comes from different components. And all that we're going to do to prove that is we're just going to look at a particular triple where A and A prime come from the same component and B comes from the different component. All of these things will work when you have more than 2 Gaussians, not a big deal. In fact, these things will even work when you're not actually spherical. That's a whole other story about isoperimetry, because what you end up doing is you end up projecting onto some medium dimensional subspace in a way that things that are not spherical become spherical, and then you can apply these techniques. But this is the meat of the argument, is in understanding this type of reasoning. And you want to show that with high probability, that this pair of points is much closer than this pair of points. And if you can show that with high probability, then that implies that over all of your samples, you really will have the property that there's some threshold tau below which every pair, which has distance less than that, actually is from the same Gaussian, and every pair with distance larger than that is from different Gaussians. So in that way, you can sample. But the important thing is that it's actually the major term about the distance between here and here will actually match the major term about the distance from here and here. And it's actually the variance term and the deviation from the expectation which is going to allow you to do things up to n to the 1/4. So Dasgupta's original paper did A, Aurora and Canaan, and then Dasgupta and Shulman did B, and it was based on this intuition that you can still have this, all pairs of points are closer than pairs which come from different Gaussians, not based on the dominant terms, but based on the minor terms in there. So the way that we're going to do it is we're going to consider the following 4 vectors. A minus mu1, A prime minus mu1, mu1 minus mu2, B minus mu2. So we consider this set of 4 vectors, and the key claim in all of this is just that these 4 vectors are, with high probability, nearly orthogonal. Can anyone give me some intuition for the statement? Does it seem true?
I mean, in high dimensions, basically everything is orthogonal.
That's right, right? There's only one vector which is not random. That's mu1 minus mu2. So all you have is you have this one fixed vector, and then you have these vectors which we described are really just random points on some high dimensional sphere. And certainly this pair will be nearly orthogonal because they're just 2 random vectors, right? It's the same way that when I said when we choose random dictionaries, they are incoherent with really great parameters, is because random vectors are orthogonal. In fact, it's even stronger because if you have one fixed vector and a random vector, as long as that random vector is oblivious to what this fixed vector is, then it still is incoherent and they have low inner probability. So that'll actually be the mechanism by which we estimate these distances, is by assuming that these vectors are orthogonal, or rather that they're nearly orthogonal, and that'll give us a way to think about what a minus a prime squared is. So let's do that now. Let me keep up only fact 3, because I think we're done with fact 1 and fact 2. So now what we can do is we can compute that, I'll do out the first one properly, even without them actually being orthogonal, just to show you what the contribution from not being exactly orthogonal is. But the way that you're going to do this is you're going to do a minus mu1 plus mu1 minus a prime, and that's inner product with itself. See, all I'm doing here is I'm taking this vector and I'm decomposing it, a minus a prime, into the sum of orthogonal vectors, because if these really were orthogonal, then the squared distance would be the sum of these squares. Now, in the case where they're nearly orthogonal, the contribution from the cross term will be very small. This is an exact equality. The contribution will be far smaller than the norm of the big contributions, but even in the deviation of those big contributions because of something like fact 3. So let's see why this is. So we can write this out now as a minus mu1 squared plus mu1 minus a prime squared plus 2 times inner product of a minus mu1 minus a prime. Now this quantity right here, we already know what this is. It's sigma squared n plus or minus c sigma squared root n log n. And the same thing is true here, that this is sigma squared n plus or minus c sigma squared root n log n. And this quantity, I claim, so we know that the dominant term for its magnitude, the magnitude of this guy, the magnitude of this vector times the magnitude of this vector, that should be sigma squared n. Because the square root of that is the norm of each of these two vectors. But because they're nearly orthogonal and they're in n dimensions, we should really divide by an extra root n. Because that's what happens when they're incoherent. The same way I take 2 random unit vectors in n dimensions, that their inner product is roughly 1 over root n times some extra polylog factors. That's exactly what happens here. So we get roughly sigma squared n times root n, really times root log n. And now what ends up happening is that this term is really smaller than what this deviation is in here. So it really is the deviation that this entire thing behaves like 2 sigma squared n plus or minus roughly sigma squared root n log n. That's the main point, right? So does that make sense? And I'll do my usual trick of changing the meaning of a constant from line to line because it'll make it easier to think about what this behaves like. But the way you should think about this is that it's really this dominant term here, the deviation, which is much, much smaller than what the dominant contribution is, that really is your uncertainty about what this distance is. Yeah? Is there a question?
Is there 2 there?
Yes, but I'm changing my constant from line to line because it doesn't really matter here.
No, the other term, sigma squared n.
Oh, sorry. That's an important too. Thank you. The other one's not so important, but roughly, the deviation behaves like that. And this is where we're going to get the end of the 1/4 round. So this is the pairwise distance between a and a prime, which came from the same component. Now let's try things which come from different components. All right? So let's just look at a minus b squared. And what I claim is that this quantity, the same way I could explicitly write it out this way. In fact, let me just do that. it'll be easier. A minus mu1 plus mu1 minus mu2 plus mu2 minus b. And then I have to write the same thing again. So this quantity now, you again have the sum of these nearly orthogonal vectors. So really what this should behave like is it should behave like a minus mu1 squared plus mu1 minus mu2 squared plus mu2 minus b squared. But again, we have this plus or minus term, which corresponds to the cross products between these, the cross terms between this. The norm of this guy is sigma root n, and then the norm of this guy is sigma root n. Only this guy is much, much tinier because it's about n to the 1/4. So really, again, the dominant term comes from this type of cross product, where what we're going to get is we're going to get a sigma squared n, times an extra root log n, but divided by root n because of incoherence. That's the main idea, is that we get a much smaller contribution here. And again, lo and behold, what's going to happen here is we again have that this quantity is going to behave like 2 sigma squared n plus or minus c sigma squared root n log n. But now we also get the contribution from mu1 minus mu2 squared, which, if you remember what this theorem is, we put in an n to the 1/4 of sigma and a root log n. So what we're actually going to get at the end of the day from this is we're going to get a sigma squared root n times a log n. That's why I chose this half power for the root log n. When I square it, I get this log n outside of the square root. And all of the other small terms have the same dominant part, but have the log n inside the square root. So this term is actually, with high probability, bigger than this term. You guys see that? So the entire algorithm now is, what I would do is I would set tau to be 2 sigma squared n. Wait, sorry. 2 sigma squared n. And then maybe plus some c sigma squared root n log n. And then what happens is that with high probability, a minus a prime squared is at most tau, and a minus b squared is larger than tau, because of this extra dominant term from the mu1 minus mu2, which gives me this sigma squared root n times log n, without the square root inside the log n. So what I've done is I've set a threshold so that with high probability, any particular pair of points that comes from the same Gaussian is less than tau. And with high probability, any pair of points that comes from different components is larger than tau. Yep? Yes. No, I would take some n to the 10 samples. But you see, my failure probability in all of this, like in fact 3, is set so that it never comes up in all of the samples, because I need this to hold for all of my samples.
So I need the dimension to grow.
What do you mean?
I need the dimension to grow.
Yeah, that's right. So I mean here, in order for this term to dominate this term, I need the dimension to be large enough that this is true. Or you can also just play with what your separation condition is, that I can just put a larger constant in front of there, so that this is also true. But this is the main idea for the clustering, is that actually B is, this B threshold is what corresponds to having mixture Gaussians where, with high probability, every pair of samples generated from the same component is closer together than every pair that's not from the same component. So all I could do is I could take my samples and I could draw a graph on them, where I put in an edge if this distance is at most this quantity, and all I would have is I would have a disjoint union of cliques, which correspond to exactly which samples were generated from which components. And then this gives me a way to realize Dasgupta's plan, find the true clustering in high dimensions, and output the empirical mean and empirical covariance in order to estimate the parameters. So are there any questions about this?
So basically what's happening is that the spheres intersect, but we're not actually going to...
We never get a sample from the intersection region. Yeah, exactly. So A corresponds to the spheres are disjoint. B corresponds to the intersection has negligible volume. What we really just proved is that that intersection region would be things where you get a confusion, where there really is a pair of samples from different components that are closer than some pair of samples from the same component. What we just proved is that the volume of that intersection region, the density assigned to it, is inverse Pauli, because this condition holds with high probability. So based on, for example, playing with what the constant is in front of this separation, what you're doing is you're driving that to any inverse Pauli you want. That's the important point to answer your sort of dimension scaling thing, is that just by playing with the constant, you get better and better with high probability bounds. But this actually is the threshold where such a distance-based clustering fails. When you have smaller separation than this, you really will get samples from the intersection region between the spheres, but that's because you're not looking at the separation only along the right axis. So if you look at the separation between mu1 and the vector connecting mu1 and mu2, then actually if you look at which one is closer to mu1 on that line versus mu2, those will actually still separate the two Gaussians. And next time we'll show a simple algorithm that'll actually recover C's guarantee. Are there any other questions about this?
Is it experiment when sigma is scaling with n?
Sorry, what?
When sigma is scaling with n somehow? Is there any?
Oh, but here sigma can be a function of n if I want it to be. And this bound, what I'm really saying is that if I put 100 in front of this, then the with high probability statement holds, so that I can take n to the 100 samples and do this. And that's enough to really estimate the parameters quite well. So the tighter and tighter you need for your approximation of parameters, the more samples you take, the larger you want the constant in front of here to be, so that you never have a failure. But this really is a bound which holds for all sigma and n, that with high probability these things don't fail. So you can have sigma depend on n if you so desire for this.
Do you know sigma?
Hmm?
Do you actually?
That's a good question. So that I did not
What was the
get
question?
into. So the question was, do you know sigma? See, one of the catches here is that I've set this threshold tau to be based on my knowledge of sigma. So what'll actually be true is that you don't even, the way I've stated the algorithm right now, you have to know tau to figure out at what threshold to join pairs of samples. But it's actually not too hard to show that you can actually estimate tau from it. if you think about trying out different taus, all they do is they correspond to sort of growing out balls around different samples. Those will give you some estimates, your parameters, and only one of them will be good. So they're actually black box ways to pretend you know what tau is. The other thing is that this would actually work for mixtures of many Gaussians too. And you can also prove that it works not just for spherical Gaussians, but for things which are close to spherical. Because when you project onto some like n over 2-dimensional space, it turns out also by concentration of measure that you get something that's close to spherical. It's similar to taking a convex body in n dimensions and slicing it through with an n over 2-dimensional space, and it'll be close to spherical. So that I won't get into. That's where a lot of the isoperimetry in this Aurora Canaan paper comes in. But the important thing is what it does in the case of spherical Gaussians, and how each different phase from Dasgupta to Aurora and Canaan to Vempala and Guan is a different idea about how to perform clustering. Disjointness, nearly disjoint because you have negligible intersection, and then finding the span of mu1 and mu2 because those are the right directions to use to separate the Gaussian mixture. So we're going to finish up with how to cluster up to threshold C. And then what I'm going to do is I'm going to show you method of moments-based approaches that have no notion of clustering. They can learn the parameters even when the Gaussians are not well separated. So the important point I want to sort of emphasize, this will be the last thing I say, is that it's natural to think that the most interesting types of Gaussian mixtures you can learn are ones where the components have negligible overlap. Because those are ones which, when you learn the parameters, you really can figure out for each sample which component generated it. Now, this notion of being well separated is just one notion which guarantees that the components are far apart. But are there Gaussians which have negligible overlap that are not well separated? Any ideas?
If the covariance matrices are really different,
so there's zero separation, but they're statistically extremely far apart. Almost every sample, you know exactly which one generated it. They have no separation. So what we're really working up towards is algorithms which learn the parameters, not through clustering. They work with no separation condition. They work with no overlap constraint. But they learn the parameters, because once you learn the parameters of something like this, then it means that you actually can use those parameters you learned to do clustering whenever it's possible, not just under well separation conditions that allow you to do distance-based clustering. So you're clustering here, what you would do is you would project onto this line and you would take a small interval. And that would be a way to cluster. But the only way that you would ever know that that's what you should do is if you actually learned the parameters correctly. So that's what we're ultimately working up towards. Now I must disappear.
What about a super quick question?
Uh-huh.
I know it's not like super crucial, but
Sorry, let me just call
Yeah.
my cap and then...
no worries.
Some like learning stuff. Yeah, after lunch.
Okay. Brendo, do you mind walking and talking, or what's the quick question?
It's fine.